Okay, this is going to be the last video of multiple integrals. In the last video, we went through the Jacobian of a transformation. Recall that the Jacobian of a transformation in R2 turns out to be something like this. Now, x is a function of u and v, y is a function of u and v as well. U and v are the coordinates of the new system. Now, with this setup, I explained you earlier, the Jacobian is defined like this. And also note that if you swap these variables, like if you place u v at the top and x y at the bottom, then it will be exactly the reciprocal of this one. Therefore, depending on the computational simplicity, either you evaluate this one directly or you evaluate this one. If this is easier for you, you evaluate this one, then get the reciprocal to find the value of this, right. So, we will take up an example, simple example, just to see the role played by the Jacobian. Now, in this case, say there is a metal sheet, the sheet is between these two lines, the boundary of the sheet are defined by these 4 lines. However, the surface density of this sheet varies from point to point, and it is given by this one. It is given as grams per square centimeters. That means the length or unit, length is measured in centimeters. Now, with this setup, it is hard to use the rectangular coordinate system. You can do it, but then you have to break this into 3 parts and do it. Therefore, we will go for a coordinate transformation. You can see that these two are parallel, and the third and the fourth lines are also parallel, right. Then, if you take this one, for example, this x plus y is equal to 1, the next line is x plus y is equal to 3. Now, if you take one coordinate as x plus y, you know that if you take x plus y is equal to, y plus x is equal to some u, u is the intercept here. So, if you want to increase y plus x, that means you have to move this way, so that you increase the intercept, because y plus x is equal to c. If you take it like that, to increase c, you have to increase the intercept, y axis intercept. So, you have to move like this, so that even though you stay parallel to this line, the intercept goes up like this. Therefore, y plus x increases when you move in this direction. Similarly, if you take y minus x is equal to c, then if you take x to the other side, you have y plus x, y is equal to x plus c. So, with that setup, the gradient is 1, you can easily see that the gradient is 1, and the intercept is c. Now, again, so y minus x is equal to c. If you take that straight line, if you want to increase c, you have to move this way, while keeping this line parallel to the previous line, this line. If you move this way, you can increase the intercept. That means, if you move this way, y minus x increases. Then you can see that if you take y plus x as one coordinate, y minus x as the second coordinate, you can see that this has that orientation. If you take this coordinate as u, the other coordinate as v, you have the same orientation as x and y. Therefore, this can be taken as your first coordinate, v can be taken as the second coordinate. Therefore, this way you increases u, this way you increase u, So, u can be y plus x can be taken as u, and the other variable, the variable which increases when you move along this direction, can be taken as v. So, this is v, right. After that, you can see, you can make this important observation. Rather than making x and y the subjects, these already, u and v are given in terms of x and y. As I told you, like depending on the computational simplicity, you can either directly evaluate this one, or you evaluate this Jacobian, and then by taking the reciprocal, you evaluate this one. You can do it in either way. Since here u and v are expressed in terms of x and y, you go for the Jacobian, which has terms like partial u over partial x, partial u over partial y, like. Therefore, you should come to the top. U and v appear at the top, x and y appear in the downstairs. So, as we observed earlier, u should be there in the first row, v should be there in the second row, x should be in the first column, v should be in the y should be in the second column. Now, you can easily find partial u over partial x, which is 1, right, keeping y as a constant, you get 1. Partial u over partial y is 1. Then partial v over partial x should be minus 1. Partial v over partial y, 1. Then you can evaluate this determinant. It is 1 minus minus 1, which is 2, right. And at the same time, you can do the coordinate transformation for this surface density. Surface density is this one. So, you can factor this x minus y times x plus y. You can see that x minus y is minus v, this is u. So, it is minus v times u plus this 8. After that, we can straight away do this in new coordinate system. However, the area of the infinitesimal element is not du dv, it is not equal to du dv. If you do it in that way, you are going to make a mistake, it is wrong. It should be like this. Remember, in cylindrical polar coordinates, unlike the rectangular coordinates, you had a multiplication factor rho. There you had the area of the infinite element was rho d theta. Likewise, you might get a scalar factor in front of du dv. That scalar factor is this Jacobian, right. So, you have to introduce that Jacobian here. However, there is a little problem. We do not have this one. Instead, we evaluated the other one, this one. Look, we evaluated the reciprocal. Later, we will take care of that. For the time being, we will keep it like that. Then, mass of the infinitesimal element. Now, the surface density is given. Therefore, once you know the area, if you multiply the area by surface density, you will end up with the mass. So, the surface density is taken as sigma. It is again a function of u and v. Now, this is the surface density. Now, we are going to find the total mass. So, you evaluate this, or you integrate this infinitesimal mass over the area A. This is the area. Now, what is this? We will see what this is. After you introduce this coordinate transformation, now look, u is y minus x. Now, this line is u, u is y plus x, yes, this is u. So, here this line in the new coordinate system appears as u is equal to 1. This turns out to be u is equal to 3. Now, u is like this, v stands like this. So, it is u, u is equal to 1, represents this straight line, u is equal to 3 represents this line. Similarly, y minus x is v, therefore, this is v, v is equal to 0, v is equal to 1. So, that area is between v is equal to 0 is u axis, this is v is equal to 1. So, the area bounded by these 4 straight lines is this one. So, in the rectangular coordinate system, the sheet appears like this. However, in the new coordinate system, it appears in a different manner. Now, you have to integrate that over this area. So, here it is easy, the limits are all constants. So, u goes from 1 to 3, v goes from 0 to 1, right. So, we have to integrate that over the area A, right. Now, assign the limits. Limits are from you know u is equal to 1 to 3, v from 0 to 1. Now, at the same time, you have to replace this guy, the surface density 8 minus uv. I put the minus sign in the middle, so 8 minus uv. Now, we need to deal with this one. The Jacobian is this. However, we did not evaluate this one. Instead, we evaluated the reciprocal. Look, therefore, the Jacobian is 2. Sorry, this one is 2. So, the required Jacobian is half the reciprocal. Now, you have du and dv. Now, it is a simple double integral. I mean, simple means easy, right? A double integral that can be taken care of very easily. Now, you know you put a pair of braces for the sake of clarity. Now, you pay attention to the integral which sits inside, right. Now, you pull out this half. Now, when you integrate it, you get 8u. When you integrate the second term, you know you have to keep v as a constant, right, because when you have several variables, it is like the opposite of the partial reverse of the partial derivatives. You keep the other variable as it is, or you treat it as a constant. So, you have v, when you integrate this, you get u squared over 2 up there. Then the limits are from 1 to 3, right. Now, you evaluate this one, you plug in the limits. First, you plug in 3, you get 24 minus 9 over 2 times v. When you plug in 1, you have 8 minus half v. Now, you simplify, you will get this one. It is a simple integral. You pull out 4, so 4 over 2 is 2. Now, you integrate this, then you will end up with this one. Then plug in the limits, the answer is 7 grams, because it is a mass. Here in this problem, mass was measured in grams. Now, there are a couple of things that I need to tell you. Now, when you figure out a transformation, actually you do not have to do this one, right. You do not have to do this one, but if you do it in this way, if you find the real orientation, then you have a nice right hand coordinate system, and at the same time you will get a positive value for the Jacobian 2 and then half. However, for some reason, say you arbitrarily choose this as v and this as u, then what happens is in the Jacobian you have changed 2 columns or 2 rows. Because of that, I mean as a result of that interchange, you get a negative sign here. Then you might think how you get a negative sign when you have an area. Area cannot be magnified by a negative number. Here what happens is that you have not taken this orientation correctly, that is why. But you can do it a problem like that without considering this. You simply take this as v and this as u and find the Jacobian. In that event, what you need to do is that you get minus 2. Minus 2 cannot be a scale factor there. Therefore, you ignore that minus sign and get the modulus of it. That is all you can do. I mean, rather than going through this painful process, I mean, you can simply take one like by looking at this, you can take this as V, this as U, or this as U, this as V, whatever, it does not matter. But if you do that, you might get a negative sign here. That means you have not considered the proper orientation of the coordinate system, but that is okay. For the sake of computation, you can I mean, you can sacrifice that. However, if you do that, you might get a negative sign. Then in the integral, you cannot put a negative sign. So, you have to put the modulus of that. You can put a modulus sign and put the positive value there. So, basically that is what I wish to pinpoint using this problem. So, sometimes you might get a negative sign if you do not consider this orientation. But here, since we have considered the orientation of the new coordinate system, you do not encounter a problem as such, right. So, any problem like this can be converted into new coordinate system, so that you get find limits like this. Here, without this coordinate transformation, if you try to do it, you might end up with 3 double integrals, which might be little cumbersome. But here it is not like that. You can make your life easier by using something like, I mean, using a coordinate transformation of this sort. Okay, all right, thank you.